This podcast is supported by the Icahn School of Medicine at Mount Sinai, an international leader in research, education, and patient care. The medical and graduate school is part of the Mount Sinai Health System, one of the largest academic medical systems in New York City. Ranked among the top recipients of NIH funding, researchers at Mount Sinai have made breakthrough discoveries advancing the health of patients. Here, clinicians and scientists push the boundaries in cardiology, cancer, immunology, neuroscience, genomics, geriatrics, environmental medicine, and artificial intelligence. The Icahn School of Medicine at Mount Sinai, we find a way. This is the Science Podcast for January 29th, 2026. I'm Sarah Crespi. First this week, how do we protect astronauts in deep space from cosmic radiation? Freelance science journalist Ailey Dolgin joins us to discuss what we know about the damage from these high-velocity particles. We also chat about deep space research being done on the upcoming Artemis II mission, which will take astronauts the furthest away from Earth so far. Next on the show, modeling the fall of fossil fuels during the decarbonization of our energy systems. Researchers Emily Grubert and Joshua Lappin wrote a policy forum on predicting choke points in the decline of fossil fuel networks. In effect, when might a system get too small to maintain its function, and how can we prevent unexpected failures? As soon as this coming February 6th, the Artemis II mission could launch, and it will loop around the moon with 4 crew members and come back to Earth. Astronauts haven't ventured as far as the moon since 1972, and this will actually be the furthest out in space any astronaut has traveled. This Week in Science, freelance science journalist Ailey Dolgin wrote about efforts to protect people from radiation once they leave the shelter of Earth's magnetic protection. Hi, Ailey. Welcome back to the show.
Hey, thanks for having me.
So what's different about the space once you kind of leave Earth's orbit and our magnetosphere? What are the risks out there?
Well, the key thing, as you said in the intro there, is radiation risk. So we've now had hundreds of astronauts who've gone into low Earth orbit, whether it's a quick visit on one of these private spacecrafts or longer missions to the International Space Station. So we know what life is like in weightlessness. But at that height, you still have a lot of protection from this magnetic cocoon we call the magnetosphere. But you get out farther, you've got all these new threats from galactic cosmic radiation. This is kind of a low, steady trickle of pretty energetic particles that are thought to have originated from, I think, supernova and other kind of celestial physics events. Then there's also the risk that the sun could basically have one of these solar storms. And if that happens, it's a huge burst of energy all at once. So those are kind of the two main risks once you get farther from Earth.
We've studied low gravity's effect on bones and other health issues, but there's not a lot of data out there about going out to the moon. Dozens of people have done this moon trip, but what do we know about how their health was impacted by these other dangers?
Really, there were only these 24 people, the Apollo astronauts, who have been that far out to the moon in the late 60s and 70s. It's not a huge sample size. We know they had some weird health things, like they would report these flashes of light. It's not light, it's actually just the radiation kind of penetrating their retina, these galactic cosmic rays. So that was kind of a weird thing. They would get cataracts, but for the most part, they seem to have come back okay. Buzz Aldrin, the second guy on the moon, he just celebrated his 96th birthday.
They do pick them very healthy, I will say.
Well, that's the thing. It's a biased sample. So I looked up the median life expectancy of these guys, and they were all guys back then, and it was like 87.5. So yeah, they tended to be fine. Of course, they were only up there for a maximum of 13 days. That was the longest Apollo mission. And this mission, Artemis II, is only 10 days. So they'll probably be fine. One of the big questions I wanted to look into was, as we think about going back to actually settling the moon and eventually Mars, and the missions get longer, well, then the exposure, the radiation risk gets larger. And so then this presumably becomes a much larger threat.
Right. And unfortunately, these circumstances aren't really easy to replicate here on Earth. So what are people trying to do? How are they trying to mimic the scenario here to test different approaches?
We can do simulations of it at particle accelerators here on Earth. probably the best equipped lab is at Brookhaven on Long Island, where there's a NASA affiliated facility where they allow you to have cells and mice and to do actual kind of biology experiments. That's one thing that not everyone who runs a particle accelerator wants to have in their facility.
No mice in CERN, I hear.
No, that's true. None in Geneva. But the main thing there is that they simulate, say, a whole trip to Mars in a day or a few hours. And they, one after another, will subject the mice to one kind of radiation source and then another. It's kind of the best we can do currently here on Earth, but it's not exactly the same as this chronic, steady, low level, constant bombardment that you're getting in space. So, really, those Apollo astronauts are our best actual experiment, but we do what we can here on Earth.
So what's the plan for the Artemis 2 crew? How are they being protected from this? Like what's in place for them?
So the main protection for them is in the design of the spaceship. They have something called a storm shelter. If there's a solar storm, they'll get maybe like a half an hour or an hour warning, and they'll all basically crawl into a space under the floor. I think it's about the size of a car trunk. And one of the astronauts I spoke with, actually, this Canadian guy, Jeremy Hansen, I think he's 6'2", maybe 6'3". He's big.
There's not upper limits on height going into space.
He might be the tallest. They'll have to cram into this space to sort of ride out the storm. And so they're inside this car trunk, essentially, that's packed with all of their gear around them. And the gear helps to absorb the radiation that's coming from this solar event.
Is the idea there just to get more and more mass between you and the storm?
Yeah, and a specific kind of mass, actually. You want these hydrogen-rich materials, which, our clothes and other kind of things are.
Okay, well, let's talk about future plans, like the research that's being done in this space. And you do talk about personal shielding. So basically, shielding the entire spacecraft might be very expensive in terms of adding more and more weight and then requiring more and more fuel and all that stuff. So what about just shielding the people? How would that work?
There's a company I spoke with called STEMRAD, and they've basically designed this protective vest. So it's kind of a big, poofy vest full of these hydrogen-rich materials that an astronaut could wear, and it protects their core organs. And if they have mission-critical tasks and they can't stay in that tiny storm shelter, they could go out wearing this thing and hopefully at least have some protection. They actually tested this thing on the precursor to the Artemis 2, the Artemis 1. Very creative naming. And they had two mannequins, one named Zohar that actually wore the vest, and one named Helga who did not.
Poor Helga.
Yeah, she got more radiation because she didn't have the vest. They had little radiation sensors on her. So they were able to do some experiments to see how protective the vest would have been. On future trips, this could be a really helpful thing. You just kind of hang on the wall, and if you need it, you need it.
Let's go to the biology side. How are researchers thinking about preventing damages using biology? There's a lot to explore here. So let's start with my favorite. This is the tardigrades.
Yeah, well, there's sort of a whole hierarchy of biological interventions, from some of the kind of more out there ones that would require a lot of thought about how to deploy it medically. And definitely the tardigrades fit in that.
Yeah.
These are these adorable little creatures that probably seen pictures of. They look like little bears. They're called water bears. They have this ability that they've evolved because they live in these ponds and they dry out, and they have to withstand strong desiccation and also super strong radiation. So they have all these molecular tricks that scientists are now hoping to recreate perhaps in us, in people, in astronauts. One of the proteins that a lot of people are looking at is one called DSUP, damage suppressor protein, with the idea that if we can harness this protein to protect our own genome, well, then maybe we could have tardigrade-like superpowers.
Right. So this is a protein that just binds kind of randomly to DNA and shields it, like literally just shielding your DNA from incoming radiation. How would they test that? How would they look into that for people?
Well, they've introduced the gene for this protein into all sorts of creatures, including green algae that flew on Artemis 1 and went all the way around the moon for 25 days.
Wow.
And sure enough, yeah, it seemed to help a little bit. And they put it into mice and all sorts of things. So it does have these protective effects in cells, in models. But as you say, it kind of has this indiscriminate glomming onto the DNA effect. And we don't really know what the downsides of that are. There's some research suggesting that it damages neurons when people have done some experiments in that. It intuitively seems like this probably is not great.
It might interfere with the daily business of the DNA, right? Like it needs to replicate, it needs to be transcribed, like all that stuff. And of course, the other problem is it's almost every cell in the body has DNA in it. Are you going to really deploy this across, or could you be selective and just say we care about these guys, we're going to focus on those?
There have been some research delivering the protein as mRNA, kind of like the COVID vaccine. You inject it into the body and it just produces the protein transiently. And they've shown that that can be protective against radiation. So people are playing around with this. And that's just one of these kind of hardy microbes that people are looking to emulate. There's another bacterium that has the affectionate name of Conan, the bacterium, Deinonychus. That one has some interesting proteins. And one of the researchers I talked to was going out to the Marshall Islands, to the Bikini Atoll, where the US government had tested nuclear bombs back in the 40s and 50s, and is kind of just on a scavenger hunt looking for more hardy microbes that maybe have other molecular superpowers.
That's very cool. Okay. What other approaches are people pursuing?
There's more conventional drug development. There are companies that are trying to develop novel drugs where the lead indication that they're focusing on is actually, something space related. And often they have funding from NASA to do that. The sort of lowest hanging fruit would be more of the off the shelf drug variety, oftentimes kind of like antioxidants and nutraceuticals. There's a trial happening right now at the University of Pittsburgh where they're testing a plant derived compound called Kempferol. And the idea there is that it seems to have some sort of mitochondria boosting properties. So these are the little like power factories of the cell. Studies show that they don't actually rebound all that well after astronauts go to low Earth orbit. These researchers think that by using this drug that has a very long safety track record, maybe that could be something that would be beneficial. So sort of more of a in the supplement variety.
And the last one I want to talk about, this is inducing torpor, hibernation, suspended animation. If you're a sci-fi fan, that's something that we know more and more about in animals. But normally they do it in space movies because you're going a long distance. And so you want to kind of preserve the person and have their biology slow down so they don't age as fast or they don't need as much food. But how would it help with exposure to radiation?
Yeah, we're not on Planet of the Apes anytime soon where we've woken up and,
We're just-
damn you all to hell. No, but this is actually kind of has a lot of appeal. We know that when animals are in hibernation or torpor, their body temperature goes down and critically their metabolism slows incredibly. And when you're in that state, when your cells and all the biochemical processes are just kind of as low at levels as possible, then there's less opportunity for things to go wrong. And so when the radiation hits that, it's just a lot less likely to cause inflammation, to cause DNA damage that would cause cancer. And so it does put animals, and perhaps if we can find a way to induce it, humans, into this resistant state. The challenge is figuring out how to do that safely.
People are looking into this. It's not just imaginary experiments, right?
You can take like an anesthetic. It's kind of like a medically induced coma, if you will. Of course, the risk benefit ratio has to be considered. But they did a trial a couple years ago at the University of Pittsburgh where they gave people kind of a light sedative, let them sleep for 20 hours, then woke them up and put them through a battery of tests. And sure enough, it slowed their metabolism by 30%, I think. Their temperature dropped a little bit. It's still a long way from true suspended animation, but it's one of the first steps in that direction.
This is all in progress research here on the ground, but there are some studies being done with Artemis 2, the mission itself. What's happening on board and what do you hope to learn?
Yeah, one of the key biology experiments happening on Artemis 2, obviously there's a lot of physics and engineering, but in terms of the biology side of things, there's a project called Avatar. This involves little organ on a chip models. So these are these little microfluidic devices, probably about the size of a thumb drive. What they're doing is they're taking blood cells from the 4 astronauts who are flying on Artemis 2, and they seed them onto these chips, and they create essentially personalized models of each astronaut's bone marrow. And this is kind of a validated model. It really does behave like bone marrow. They're going to make 2 chips for each astronaut. One will stay on Earth, and one will go up with the astronaut to space.
Oh, a twin study.
Yeah, it's kind of like that. And what they'll be able to do is then compare the effects of the mission, and especially of space radiation, on the chip and compare that to the astronaut's blood, looking at all sorts of molecular markers of stress and aging and mitochondrial function, all the kind of usual battery of tests. And the idea here is really, as the name implies, like, do these chips serve as avatars, as stand-ins for the astronauts? And if they do, if then in the future we could just fly one of these chips up into space ahead of a mission, see how it responds, and then by analyzing it, we can design personalized medical kits essentially. You could pick your antioxidants or your targeted drugs or whether you need tardigrade proteins or what have you, all based on first sending up this little facsimile of your bone marrow.
You end your story with people drinking wine from, I guess it's space wine. What is this?
Okay, it was not people, it's just me.
You had it. Oh, you had space wine. Oh.
Yeah, so this was a quirky little thing I felt like I just wanted to get in there.
I mean, there's real science here. So on the first test run of Artemis 1, they sent up a few different microbes to evaluate the effects of deep space on green algae, on mold, and on yeast, like baker's yeast. So I grew up in Vancouver. I was going out to visit my family, and I saw that the main researcher for the yeast experiment happened to be at the University of British Columbia. So I called.
Yes.
Yes. So I was like, all right, I'll pop out for the day and just chat with him. I wasn't thinking much of it. And we're sitting there chatting in his office, and he mentions that they made wine with the space yeast, which ostensibly was just kind of a test of yeastiness, essentially. Like, they saw that going to space caused mutations and caused all this molecular stress. And they just wanted to know, like, can the yeast still do what yeast do? And a good test of that is, can it ferment and can it make wine? I was like, well, have you tasted it? It turns out the researcher doesn't drink
Oh,
for whatever reason. So he's like, no. I was like, well, can I taste it? And he was so unprepared for that question. He was like, okay. And turns out he had like little 2 jars on his bookshelf there, and he pulls them up and he's about to serve me the space wine, like literally in the cap of his Gatorade bottle because he doesn't have a glass. And I was like, no. We got to do a taste test. He's like, oh, yeah, that's a great idea. So he runs off to the break room and he comes back with a couple of coffee mugs. I kind of twist his arm to give me a blind taste test, and I taste them. And I should say, none of the wine was good.
I was going to say.
Well, because this is like the lab workhorse of yeast genetics. It's not exactly the preferred strain of the Napa Valley. One of them had this like really kind of bitter aftertaste. So I wouldn't say either was good, but one was definitely bad.
Was it the space wine?
Well, yeah. So I was like, well, that one's kind of bad. And this one is, it's okay. It tastes kind of like a muscadet, like a dessert wine.
Yeah.
That's the space wine. You said the space wine was better. And he was so happy. I like made his day.
Definitely need to replicate this experiment.
So I don't know if, one of them just aged badly after sitting for a couple years on his bench,
or if there's really something to this. But yeah, the yeast that went to space yielded a better tasting wine. So I don't know what that means.
This adventures in science reporting.
Exactly. So that was super fun.
That is awesome. Okay, thank you so much, Ailey.
Thank you for letting me talk about my alcoholic tendencies.
Ailey Dogan is a freelance science journalist. You can find a link to the story we discussed at science.org/podcast. Stay tuned for a segment on modeling the fall of fossil fuels with civil engineer and environmental sociologist Emily Grubert and historian and engineer Joshua Lappin.
No one goes to Hank's for his spreadsheets. They go for a darn good pizza. Lately, though, the shop's been quiet, so Hank decides to bring back the $1 slice. He asks Copilot in Microsoft Excel to look at his sales and costs and help him see if he can afford it. Copilot shows Hank where the money's going and which little extras make the dollar slice work. Now Hank has a line out the door. Hank makes the pizza, Copilot handles the spreadsheets. Learn more at m365copilot.com/work.
Apply today for a chance to win the Science and SciLife Lab Prize for Young Scientists. This annual prize recognizes outstanding doctoral research in life science, including cell and molecular biology, genomics, proteomics, systems biology, ecology and environment, and molecular medicine. Apply today at science.org/prizes for a chance at the $30,000 grand prize. Submissions close July 15th, 2026. For its 2025 Breakthrough of the Year, science actually named the unstoppable rise of renewable energy. The world now gets more electricity from renewables than coal, and wind and solar are still very much on the rise. But emissions are still going up, and renewables only account for a fraction of the entire world's energy use. We're going to talk about what happens to our energy systems as we decarbonize, with emphasis here on systems. Production, distribution, and consumption of fossil fuels. This is all intricate, expensive to maintain, and not particularly easy to downsize. Joshua Lappin and Emily Grubert wrote a Policy Forum article on this transition this week in Science. Welcome to the podcast, Emily. Welcome, Josh.
Thank you so much. Glad to be here.
Thank you.
As a non-expert, it makes sense to me that we need to plan for the decline of fossil fuel use. Just like we tried to plan or encourage in various ways with regulation, policy, incentives to increase the use of alternative energies. I don't know much about the specifics. What are some of the risks of shrinking fossil fuel systems?
I think it's a really good question. And it's something that I think Josh and I have the experience of being some of the small but mighty community of American energy resource researchers that really focus more on fossil systems. And the reason is precisely like you're talking about. The notion of planning makes a lot of sense, but how you actually do that and why you need to do it specifically for fossil systems. And we essentially argue that you don't see situations where the fossil system is going to do this on its own. And some of the consequences of that are really significant safety issues for people and also just the ability to get the services that you need. So if you don't plan for how to close things, they might, first of all, not close, or they might close very chaotically. And there are a lot of risks associated with that.
If all of a sudden a bunch of things close that were providing energy to your neighborhood, for example, or the shipping, everything gets more expensive. Is that one of the concerns, that things will be more expensive until we replace them?
Yes, absolutely. One of the possibilities is skyrocketing energy prices, and a cost crisis affects the people who are most dependent on those services and who are least able to leave those services behind. So there's a really regressive effect on the people who can least afford to substitute, for instance, gasoline for an electric vehicle, or who can least afford to hail a ride. That's one set of concerns. But there's another set of concerns about actually whether energy services will be available at all for any price under some circumstances. This looks different in different fossil systems, but we think it's actually pretty intuitive. The one we like to talk about in these circumstances most, because almost everyone interacts with it on a daily and a weekly basis, is the gas station. We are all dependent not just on the existence of a gas station, but the existence of an entire network of gas stations.
If you switch to an electric car maybe 5 years ago, you're going to have trouble driving across the US. I had friends who tried it and who were like, yeah, there were a few stumbling blocks. The network wasn't there. So imagine now that's ramping up, and then this gasoline supply is not ramping down in an equal and well-distributed way. It's patchy, maybe expensive, or not there at all in parts of the country.
Oh, absolutely. As things start to decline, one of the ways that our current system sort of encourages something to stay open or not to stay open is whether it's profitable. And one of the big arguments that we make is that as you get to the point where some of these systems aren't expecting to be in a growth scenario anymore, you can't rely on demand being there for a long time. The facilities that remain profitable aren't necessarily the ones that you need to provide service continuity. And so this also points to, we need to plan this.
And I like that you have this table where you kind of bring up these problems. I guess you'd say, like, you can't go to the convenience store anymore.
Right. Where are you going to get your hot dogs? Like, honestly.
What about my slushie? And what about my tire air?
Yeah, genuinely, right?
Yeah, I think this is super interesting. The other thing I wanted to ask about is this kind of main idea that you focus on in your paper. There's a lot of modeling being done on scaling up and scaling down these systems, but these models seem to be missing what you call minimum viable scale as a factor in understanding how these drawdowns will work.
Minimum viable scale is the category that we've offered here to unite a variety of different limits that emerge in complex networked systems that can prevent them from shrinking linearly or manageably past a certain point.
Something is shrinking in a predictable way, and then it gets to a certain point and it's no longer possible. It's not going to be available for whatever reason. Let's get into some specifics, some examples of this.
We've broken minimum viable scale down into a set of types. We talk about physical minimum viable scale, which has to do with throughput and operational limits that are actually design properties or emergent operational properties of the physical systems themselves. We talk about economic minimum viable scale, which has to do with the way that we finance infrastructure, and we finance in particular its maintenance and operations over longer periods of time. And then we also talk about managerial minimum viable scale, where we identify types of constraint that emerge because of either operational cultures or decision-making boundaries. The big example there that we think will be familiar to people, but isn't often considered in the context of energy system planning and climate policy, is antitrust. It's actually illegal in many cases for the operators of big fossil fuel assets to coordinate with each other.
To make it a little bit more concrete for people, like you talk about coal mines and how a coal mine is supplying locally to electricity generating plants. And if a bunch of them go offline suddenly because the demand is down, people are switching over to renewables, the mine might close. But then that means that mine, which makes coal that it can't be shipped all around the world, it has to be used like by a plant designed to use it, that might suddenly shut down. And there's this back and forth, and having them cooperate, communicate is not necessarily in their best interest today. But as things go further, as things decline in an unpredictable way, either on the mining side or the generation side, you're going to have to be more coordinated.
I'm super glad you bring up that example, actually. So a lot of people don't know this, but there's like 10-ish big mines in Wyoming that supply about half of the country's coal. And when we went to look into, just like what you're saying, how many generators would actually have to shut down to make it so that we don't think that those mines could continue to operate. And for people that have been out to northeastern Wyoming, they're enormous. The biggest of those mines is about 8 miles across. But what we found there is that it's actually a shockingly small number of generators that would need to close to change the demand for that mine so much year over year that it might not stay open. And so that's basically where we're getting at this minimum viable scale thing.
And you talked before about these schedules, like there are all these decision points in these giant pieces of infrastructure where they're like, we need to redo our plant. We need to clean up these pipes. We need to invest money in them. And if you know 5-10 years from now, you're not going to be using any of this, why would you do that?
Exactly. It's really expensive. Like if you look into maybe spending $100 million to keep a plant open that might need to shut down in 2 years anyway, like it's really, really noticeable that you stop investing in those ways, which means also back to this point about why minimum viable scale is a way to identify risks. I think there are a bunch of issues where we're essentially encouraging the system to run to failure.
We're just decreasing demand without kind of managing supply in a way that doesn't just crash. Is that kind of what you're getting at?
Part of it, yeah. And I think one of the other things that we look at is just that historically speaking, we have seen that even when you do have these big breakthroughs with renewables, which I don't want to, imply that that's not a big deal, but we haven't necessarily seen a corresponding set of closures that imply to us that there's actually a replacement going on.
This is really interesting from the risk side, where you're talking about the backlash that you could face if we do see these spikes in the price of fossil fuels as renewables kind of ramp up. That's also going to be industry clinging to life.
Oh, yeah, absolutely. And you're taking a very, very powerful industry with a relatively small number of assets, which in some ways confers maybe more political power than you see with something where you have very, very modular systems that can be built in lots of places, which is a huge advantage for renewables. But when you've got like a fossil system that is basically providing half of the funding for a town's K through 12 education without a plan where you're explaining how that thing is going to turn off, and maybe it's been there for 100 years, like they're already at end of life in a lot of cases, which is a nice thing about the fact that the US's infrastructure is old. But without a plan for what happens next, it's probably not going to try to go offline on its own.
I thought the detail in this paper, I wish we could go into all of it. I really liked all your examples because it really does infiltrate our lives in 1,000 different ways. And to imagine it all disappearing, like the pipelines that people fight about, once you turn off some of those, they degrade, and everybody who's left using them is going to be paying more and more. And so it's definitely a slow motion disaster if nothing is done.
One of the things that we really think is important to kind of talk about within the modeling community too, though, is that oftentimes the way that our models are set up and the way that many of us are trained is to think about it mostly in cost terms as sort of a proxy for all of these other things. And I think one of the big points that Josh and I make is that cost is one of these issues. This is also a massive unexamined safety problem because the fundamental underlying conditions are changing. And it's also, like Josh mentioned earlier, a huge issue where you might just fail to have access to certain services. So it's not just cost, it's also these safety and access questions.
It's also the case that in some cases, depending on the failure mode here, failure can be irreversible. And what we really don't want is to find ourselves in a situation where a system reaches its minimum viable scale and breaks in a way that makes it much, much harder to regain that energy supply capacity going forward.
I can't imagine spinning back up a petroleum refinery, for example.
Right.
Very small lapses in maintenance can cause immensely expensive and slow repair processes at refineries. This is something that refinery operators are already aware of, that refinery workers are constantly wrangling with refinery management about. And as margins get thinner, as more competitive pressure between remaining refineries gets introduced, the temptation to cut back on maintenance schedules grows, and that introduces new risks for workers and also new risks that these assets are going to be suddenly unavailable for long periods of time.
What kind of scale should we be thinking about here? I started with global increase in renewable use, but mostly we've talked about the US and smaller units like either industries or different types of generation. Is this something that needs to be applied all the way up and down the scale?
I think so. If we're taking climate change and all of the other things that come along with fossil use seriously, we're going to zero emissions. We can make a little bit of wiggle room on the side about net zero emissions. But ultimately, I think one of the real beauties of thinking about this as a zero emission system is that it really gives you the flexibility to think about what it means to retire the whole thing. You don't have that complicated set of decisions about what you allow to stay online, really. And so thinking very carefully about how do you sort of balance this point that some systems cannot be certain sizes with the fact that they eventually all need to go entirely offline, I think really actually opens up the design space to think about sequencing, timing, and all those kinds of things as we start to phase out these systems.
Yeah, that really plays into my next question, which was going to be, how do you work in this idea of minimum viable scale into the modeling that people are doing and the planning for the decline of fossil fuel systems?
By and large, the type of modeling that's conducted and also a lot of the policy thought that's done in this space thinks about individual assets. And that works to a certain degree. You need to have asset level attention to exactly how each asset is operated, designed, and financed. The details at that level of scale are critical. But the point we are trying to make by highlighting the phenomenon of minimum viable scale is that at some point, asset level analysis that thinks of additions and subtractions as marginal, by which we mean that one fewer plant will always have the same effect on the system, whether you're moving from 500 to 499 or whether you're moving from 10 to 9. We're highlighting that that's not actually always going to be the case in these network systems. And therefore, alongside an asset level attention to the design features of individual systems or plants, you also need to understand their interactive effects. All of these fossil systems are interconnected with each other. And oftentimes, an event or a closure in one facility category will impact other facilities. You can see this in the refinery space, where refineries are codependent with pipelines, which are often separately managed and separately financed and separately owned. And they're also codependent with gas stations.
Shipping, pipes, plastic, all of that stuff is tied to refineries. And you mentioned this a lot. Networks of networks seems to be a really important term here. Biggest question now. What are the big barriers to getting this incorporated into the thinking and then, of course, further out into policy and regulation?
One of the ones that we tend to highlight a lot is just the way that our markets are set up in the United States really makes it very difficult to do this in a coordinated way. Your question earlier kind of touched on the point that we're fairly focused on the US as an example here. I think this condition actually applies globally, but we have some different institutional structures. In our case, there are things like antitrust and just the fact that most of these assets are actually privately operated and owned. In most of the rest of the world, critical infrastructure is not privately owned. And that means that when you have a situation where, like Josh is saying, if you're going from 2 things to 1 thing to 0 things, if there's a public interest in having one of those around, there is a mechanism where the public can actually compel that thing to stay online. We don't have that structure in the United States. And so what the barriers are largely is that at this point, when you have private asset operators making decisions independently because they're not allowed to coordinate and because it's not necessarily in their best interest to coordinate, you don't have the ability to plan. And so thinking about where is there a role for public management, as we get to the point where some of these systems that we sort of assume are going to be the backstops for the new renewable and other zero carbon resources. So it's okay if they fail because we have a little bit of gas still there to catch us or whatever. As you get smaller and smaller, you can't rely on that being true anymore. So the barriers are really about control of who stays on, when do they close, when do they stay open, these kinds of things.
One thing you talked about was the antitrust and other ways that are kind of cutting off sources of some of this information. for coordination, but even for modeling, like where do you see that going? Do you see that loosening up, or is there another source of data?
Because of the market structure in play here, it can be very, very hard to get access for researchers and also for policymakers and regulators to get access to the type of system performance and throughput data that you need to really understand exactly where does minimum viable scale take hold and how can we predict these thresholds in advance. Oftentimes, the data that you need constitutes a type of business advantage. And so companies have strong incentives to keep this data confidential. And so creating new tools for data disclosure, this in concert with the other issues that Emily was highlighting, is going to be critical for actually being able to move forward in establishing not just estimated minimum viable scales, but being able to say for this pipeline here that is critical for the health, safety, and economic productivity of this big urban region, this is when that pipeline will begin to face challenges.
Not to do the thing where I just like end on a hopeful note or whatever, but
Let's do it. Because I was going to ask you if we should nationalize the energy sector. So
yes, I have a t-shirt. It's pretty cool. Honestly, I think so. I think we've had a hard time coming to institutional models that allow you to actually succeed at a full transition in a way that actually protects people without some form of public management that probably involves enough control to be seen as ownership. But I think the really hopeful note on this is that that's a doable thing. Lots of places have done that, not necessarily for the purposes of decline, but that's the norm globally. The other thing that I think is kind of what we're hoping that people take away from this analysis is just to see we have so much information about existing systems. It's a massive advantage to be talking about things that currently exist. You don't have to guess how this system works. You don't have to guess how many people work there.
we're not sampling.
Right, exactly. We know. And as the system gets smaller and smaller and smaller, in some ways that gets even more tractable. So when we say you actually do need really detailed models of individual assets at a huge system scale, the reason we abstract that away is because that's really hard. As the system gets smaller and smaller, it gets easier. And I think that all of this is predictable, it's solvable, but we have to predict and solve it.
Oh, it's great. All right. Emily, Joshua, thank you so much for coming on the show.
Thanks for having us.
Thank you.
Emily Grubert is a civil engineer and environmental sociologist. Joshua Lappin is a historian and engineer, both at University of Notre Dame. You can find a link to the Policy Forum article we discussed at science.org/podcast. And that concludes this edition of the Science Podcast. If you have any comments or suggestions, write to us at sciencepodcast@aaas.org. To find us on podcasting apps, search for Science Magazine. Or you can always listen on our website, science.org/podcast. This show was edited by me, Sarah Crespi, and Kevin McLean. We had production help from Podigy. Our music is by Jeffrey Cook and Wen Koi Wen. On behalf of Science and its publisher, AAAS, thanks for joining us.
Meet the new iCIMS, the single talent acquisition platform that's fully future-ready. It works wherever and however you hire, with insights no one else offers. One solution that fits seamlessly into your existing tech stack, which is why IT and HR leaders trust it. With the best of enterprise-grade software and AI, iCIMS helps you identify and secure the right talent faster. iCIMS, powering exceptional hiring. Learn more at icims.com.